Okay, here is my second space mission, Asteroid launch. And so in both cases, I have a spacecraft that's landed on an asteroid. I'm going to launch it. I want to get far away with a final speed V3 of 12 meters per second. And I've changed my spacecraft. I made it 2,000 kilograms. And I changed my asteroid. Okay, so everything's the same, but now the asteroid is has a radius of only 20 meters, so it's much smaller, and it has a mass of, let's say, pick something quick, 5,211 kilograms. And the mass of the spacecraft is 2,000 kilograms. So the question is, what's going to change with the spring constant in order to get far away? And the problem is that if I have the spring pushing on the spacecraft to launch it, well, the spring's also going to push on the asteroid. And so it's going to get launched. So instead of this, it's going to do this, right? So I have to take into account the motion of the asteroid. So let's again use work energy. So I'm going to start off with, I'm not going to use momentum principle because I don't know anything about time. And then I have these 1, 2, 3. Position 1 is when it's at rest and compressed on the spring. Position 3 is far away, and so work energy doesn't care about time. So I can write down the same thing, system. It's going to be the asteroid plus the spacecraft plus the spring. It's the same thing. But now when I go, and again, there's no work done on the system because there's no external forces. And as this thing moves away, you go back and watch version 1 of the video. But as this moves away, it's going to slow down because the gravitational force is pulling it back. So I don't care about the speed of this one afterwards. I only care about the speed of that one. So I'm going to say work is the change in energy, but there's no work done, so I have 0. Now I have what's the change in energy. So I'm going to write this out as delta K spacecraft plus delta gravitational potential plus delta U spring, that's spacecraft, that's spring. And where kinetic energy is 1/2 mv squared, the gravitational potential is negative g ma ms over r, where r is the distance between their centers, and us is 1/2 ks squared, where k is the spring constant and s is the amount it's stretched or compressed. So the other term I need to add in here is, since the asteroid recoils also, it will also have a change in kinetic energy, delta Ka. So let's consider the position of this one really far away. So I know that let's write this out because some of the stuff is 0. So if 0 is Ks3 minus Ks1, the change in kinetic energy of the spacecraft, plus Ug3 minus Ug1. So the potential is the potential for the asteroid and the spacecraft. So they don't have separate potentials. It's the interaction between them. And then I have plus Us3 minus Us1 plus Ka3 minus Ka1. Okay, again, we have some things that are 0. The first thing that's 0 is that the velocities of the two objects to begin with are 0. So the initial kinetic energies are 0. So this is 0 and that's 0. This is not 0. It's moving far away. And probably Ka3 is not 0, but I don't really know. G3 is 0 because they're really far away. The gravitational potential energy decreases. So if R gets really big, then that's 0. So this is 0. And then finally, Us3 is 0. There's no energy stored in the spring when it's not even compressed anymore. So now let's write this out. I have 0 equals 1/2 ms v3 squared. I'm going to just call that v3. I'm going to do something weird. Minus this, which is negative, so it's going to be plus g mass of the asteroid, mass of the spacecraft, over r, right? That's the initial position, their r distance away. If you want, I guess I should add in that 1.6. No, it's compressed 1.6. Yeah, so that's the radius with compression. I know. It's a weird problem anyway. I can make up stuff. Then I have this minus 1/2 k s squared. And then finally, plus 1/2 ma. I'm just going to call this VA squared, where VA is the final velocity. So this is the final velocity of the thing. Yeah. Okay. I got it. I had to think for a second. So when this spring no. Yeah. Yeah. So this spring is going to push them apart. And that's going to move. And this is going to slow down as it does so. But the whole time there's two forces interacting between the mass, the spacecraft, and the asteroid. The spring pushes them apart, speeds them up, and then gravity slows them down. So I don't know the final velocity of the asteroid, but I do know this. I know that F asteroid on the spacecraft is equal to negative F spacecraft on the asteroid, because it's the same force. They're an interaction force. Whether it's a spring or whether it's gravity, it doesn't matter. So this means that the change in momentum for this is on the asteroid with respect to time, is negative the change in momentum of the spacecraft with respect to time. And the time's the same, so the change in the momentum of the two things are the same. That means the total change in momentum is zero. So the momentum before the collision is zero. So the momentum after the launch is also zero. So this is moving to the right, that one's moving to the left. So I can say, this is the trick here, I can say MA, VA, that's just VA, that's the velocity at the end, is equal to MS V3. This is conservation momentum. Okay? So now I can solve this for VA. I know exactly what VA has to be. VA is going to be MS V3 over MA. So that's going to be, let's put in the numbers, the mass of the spacecraft was 2,000, and the final velocity was 12, and this was 5211. So if I put that in my calculator, I get, I get 2,000, 12 times, and then 5211 divided by. And I get 4.61 meters per second. So now I can put that in up here, okay? And I can solve for k. So let's switch to a new paper. I'm going to rewrite that equation. So let's just rewrite this. I have 0 equals 1/2 ms v3 squared plus g ma ms over r minus 1/2 ks squared plus 1/2 ma va squared. And now I know what va is. I know what it is. I want to solve for this k term, so I'm going to add this to both sides. I get 1/2 ks squared equals 1/2 ms v3 squared plus g ma ms over r plus 1/2 ma va squared. And then I made a mistake before, so I can go ahead and multiply everything by 2. So that's going to cancel. I get a 2, cancel. Now I'm going to divide by s squared, and I get k equals ms over s squared v3 q squared plus 2g ma ms over r s squared plus ma va squared over s squared. So let's put in my values. So ms was 2,000, 12 squared, 1.6 squared, plus 2 times 6.67 times 10 to the negative 11th. I'm leaving off the units. the mass of the asteroid was 5211. The mass of spacecraft was 2,000. And then the radius was 20. And this is 1.6 squared. And then I have the last term, mass of the asteroid was 5211. The velocity of the asteroid was 4.61 squared over 1.6 squared. Okay, now this looks like, oh, you can't put that all in your calculator at once. Oh, I can. Oh, I totally can. Because I have a Hewlett-Packard RPN calculator. On. Turned on. Come on. Don't fail me now. Oops. Got it. Okay. So let's start right here. 2,000. Oh. $2,000. 12. Ah. You know, once you start bragging about your calculator and then it doesn't work, it's just a bad thing. Okay, 2,000, enter. Ah, that's wrong. 2,000, enter. 12 squared times 1.6 squared divided by. That's that term. Now this term, 2, enter. 6.67 times 10 to the negative 11th times 5211 times 2,000 times 20 divided by 1.6 squared divided by. And now this last term is 5211, enter, 4.61 squared times 1.6 squared divided by. Now I have to add these up, plus, plus. And I get a spring constant of 1.5 times 10 to the 245 Newton per meter. Okay, there's going to be another one. I'm going to make another problem like this, but I'm going to do it with momentum principle. I'm going to break it into, I don't know what's going to, I'm going to use momentum principle and numerical calculations.